Now that we know what implicit differentiation is, I think we're ready to differentiate these 6 inverse trig functions. So here we go. To differentiate inverse sine of x. Do you mind if I don't? I'm sure it's in the book. How about if I do this one? There's a bit of trick in it. So to differentiate the inverse cosine of x, then let's go ahead and say we want to start with y being equal to the inverse cosine of x, and let's find dy dx. Now, I can't use the limit of a difference coefficient definition of the derivative function because that would involve the inverse cosine of a sum. I don't have any handy addition angle identities, or excuse me, addition identities for the inverse trig functions. So instead, I'll cheat. I will take this relationship, evaluate the cosine on both sides, and I'm left with this equivalent relationship. Now, treating y as a function in x, I will differentiate y implicitly with respect to x. Now, to differentiate the cosine of anything, I get the negative sign of that thing. But the chain rule says now I need to multiply by the derivative with respect to x of whatever the innermost function was. Well, I don't know what it was. I call it y. I'm being silly. We knew what it was, but I'm pretending we don't. Differentiate the right-hand side with respect to x gives me this. But that implies dy dx is 1 over the sine of y with a sign change. But if you take a peek at what this relationship says, if I were able to be, I think I said the correct one. If I were to be able to, my goodness, I can't say this, can I? If I were to embed y as an acute angle in a right triangle, if it is an acute angle, to say that its cosine is x simply means the ratio of the adjacent side to the length hypotenuse is x to 1. Using my nifty little Pythagorean theorem, here's the length of the other side. It is not too small. That being the case, I guess I can now say that dy dx is a negative 1 over the sine of y, but the sine of y is nothing more than this over this. I guess it's just a radical expression. You and I have just derived out of thin air the derivative of the inverse cosine of x. We came up with this. Turns out the derivative of the inverse sine of x is the same thing, but with a sign change. Now to differentiate inverse tangent of x, it's just as easy. I'm going to run through a few of these because I can do it rather quickly. So if y is equal to the inverse tangent of x, and I'm interested in finding dy dx, let's take the tangent of both sides. Let's differentiate implicitly with respect to x. Let's isolate dy dx. And let's change our picture. Because if I were to embed y as an acute angle in a right triangle, to say that its tangent is x simply means the ratio of the length of the opposite side of it to the length of the side adjacent to it is x to 1. Meaning the hypotenuse has this length. That being the case, let's slip in for this denominator the secant squared of y. But the secant of y is just hypotenuse over adjacent. It's just a radical expression. But when I square it, I get this. That being the case, I do think the derivative of this is this. And you can show in exactly the same fashion that the derivative of this is the same thing with a sign change. Next on my list, let's do inverse secant. I didn't say that very well, did I? I said let's do inverse secant. I meant let's you and I derive the derivative of the inverse secant function. Well, if y is equal to this, then certainly the secant of y is equal to x. Now, treating y as a function x and differentiating implicitly with respect to x, I have the following. But that implies this. But that implies I have 1 over something. To find out what the something is, this you and I, yet again, embed y as an acute angle within some right triangle. Now, to say that its secant is equal to x simply means the ratio of the length hypotenuse to the length of the adjacent side is x to 1. That being the case, the length of this side over here certainly must be this. Again, if I'm not being too small. Let's see, another name for secant of y is x over 1. Another name for the tangent of y is this over this. Getting a little nervous. Depending on how you were raised in trigonometry, the inverse secant function was visually generated by restricting the domain of the secant function to either 0 to pi, or in the first and third quadrants, but it doesn't matter which one you're looking at. Whether you're looking at the second quadrant or the third quadrant, x could be negative. And if you look at the graph of the inverse secant function, slopes tangent lines are always positive. So no matter what your restriction of the domain of the secant function was back in trigonometry, we need to make sure that that first factor is positive. So I have the absolute values in there. Let's make it efficient. So the inverse secant has this derivative. The inverse cosecant has the same derivative with a sign change. I'll leave that for you.